All right, yeah, it's a long title. I originally planned to go kind of chronologically for the life of a finite element analyst. First you go to school, and then you show up and you at a job and you learn some of the software, and then you get to do something interesting eventually. But I think in the interest of time, I was going to just jump to the interesting part to make sure we get through that. Uh, so I'm gonna skip some of this stuff, which may or may not, we can come back to it if there's time, but get to the good stuff. So just as background, since I skipped all of it, the finite element method is it's a numerical method for approximating the solution to differential equations, if anyone's uninitiated. It's been embraced with gusto by the engineering community. It's reliable, it's efficient, and it's created a whole new industry in terms of producing software that implements the finite element method. Oh, excuse me. Um, and it's also anything that you own that has been engineered in the last 50 years has probably been touched by the finite element method. I would bet that it has been, and I would win that bet often enough. It'd be worth my time to do it. Even the razors that you shave with have been analyzed with the finite element method. I wanted to go through an example of a project that I worked on a few years ago. I work in the helicopter division, but I work in a group that gets to touch a lot of different things. And so what I want to talk to you about is what's called a frangible joint. So a frangible joint is any joint that's meant to be broken. Um, it's great word, frangible. It sounds like it comes from Jabberwocky. But the example that I have here of a frangible joint is between stages of a rocket. So as a rocket lifts off and progresses, eventually a stage will spend its fuel and it becomes kind of dead weight. So you eject it. Um, it's expensive to put mass into space, so you get rid of the dead weight. Um, it's a circumference. It's a ring between the stages. I think I have the highlighter going. There we go. And I want to draw your attention here to this photograph. So this is a piece of a frangible joint from a rocket stage, from a laboratory experiment, from a test. And where my highlighter is now, the upper left corner of the photograph, there's a lighter piece of metal. And that would be the plate that was around the circumference of the lower stage that's being ejected. It slides between two other plates of it, it looks like almost blue. Those two plates would be from the upper stage that's going to continue on. So it's the lower plate slides in between the lower two plates, kind of like a sleeve, and then it's bolted all the way around the circumference. At the top of the upper stage plates, the joint is already broken. This is a post-test photograph. You can see there's a little notch cut in the metal, and that's on purpose. That notch is cut all the way around the circumference, and that's where we want the break to happen. Inside that notch, there's a metal tube also all the way around, and inside that metal tube is an explosive. So the way the joint operates is when you want to separate, you ignite the explosive, the tube expands and it pushes those walls out, and you hope that it snaps the metal at that ligament, which is the notch is called the ligament. So in a rocket, everything is fail-safe, just about. And in engineering terms, that means every component has a job. And if it fails for some reason, there's a different component that can also do that job. A frangible joint is one of the few things on a rocket that is not fail-safe. So its reliability warrants a lot of attention. If a frangible joint fails, you lose the rocket and the payload. And we were interested in this joint here, this particular design of a joint, because it had been used hundreds of times, but only for satellites and cargo. It had never taken manned missions into space, and that is the intent. And so what we want to do is we wanted to do an analysis of the reliability of this joint beyond the 200 or 300 launches that it already worked in. And so we talk about the design of the joint, and that includes every variable in the joint and its value. It usually has a numerical value. For instance, the thickness of the plates of the metal is a design variable. the position of the tube relative to the ligament is a variable, design variable, as well as all the material properties of everything in there. There is a design, it's like the design that's on paper for this. Every design variable has a very specific value, but in production, you can never achieve that exactly. So there is an interval in which all these things reside, these variables, but you can't know in advance what they are. So like the notch, it's cut, with a CNC machine, and we can get it to say 1/10 of an inch or whatever we want to get it to, but it's 1/10 of an inch plus or minus 1/100 of an inch. Even the material properties of the components, we know they're very specific alloys. We know the suppliers. We know a lot about them. Even their density, stiffness, strength, they're known, but there's a certain amount of uncertainty. And so we have an interval in which each of these variables lies. And if we take all the variables together and their intervals and take the product of all those sets, we get a large dimensional box. And that is the design space. And so when we make one of these joints, each production is a point in the design space. And so to measure the reliability, we had to come up with some sort of quantitative measure. And we decided that for our analysis, we were going to focus on the explosive and say, well, given a design, a point in that space, what's the minimum amount of explosive we have to put in there for the joint to operate? And so we came up with about 20 variables. We split them into two sublists, geometric variables that would be, thicknesses and positions. And then also the material properties. There's a lot of materials involved, but we came up with about 20 variables that we felt had a direct impact on the performance of the joint. And we created a finite element model of this. So the finite element model solves, all the differential equations involved. There's quite a bit. There's solids in there. There's the explosion is modeled as a fluid event. There's expanding gases, all sorts of things happening. And the finite element software kind of takes care of that. We build the model and we can run it. And then what we would do is then we would iterate it. We would have a design, we'd build the model, and then we can iterate that model until we find the minimum charge that it would take to sever the joint. And we're a little bit clever about it, using a bisection method to kind of, we felt we were clever. But essentially what we're doing is we're evaluating a function when we do that. We have a finite element model of the joint. We give it a certain amount of charge and we run it, and we have to run it several times, and we can find out what is the minimum charge size for that design. And so I think one evaluation of this function would take, say, 8 to 12 hours of computer time, of wall time, given the resources we had. So it's a function, but it takes a long time to evaluate its value at any point in the domain. So our first goal given to us, I think someone else talked about whether you get to choose your problems or problems are chosen for you. And this is an instance when it's kind of chosen for us. They said, well, if something bad's going to happen, it's going to be because we're at the extremes of a variable's interval, or either one end or the other. And so why don't we just evaluate this function at the corners of the box that the design space represents? And anyone who knows anything about geometry or combinatorics would quickly tell you a 20-dimensional box has over 1 million corners. So that was out of the question. And then, someone thought, with respect to each of these variables, if we isolate one variable at a time, the function we're evaluating should be monotonic with respect to that variable. Meaning, like, if the notch gets thinner and thinner and thinner, then it should take less and less and less charge to separate the joint. So each variable definitely has a well-defined worst case value. So maybe we could just look at the worst case values of all the variables. And that we could do. We built the model for, say, the 20 worst case variables in isolation. And we run those and we find the minimum charge size. And then we think, well, if one variable could be at its worst case value, what about two? And with 20 variables, there's 20 choose two combinations of two. So that's 190 simulations. So 190 evaluations of that function, which takes, half a day each of computer time. And we do that, but then we get to 3, because it's not unreasonable to think 3 could be at their worst case value. And that's where we kind of had to stop, because 20 choose 3 is a little more than 1,000, and that's pretty much at the resources we had in terms of time would be spent. And there's no doubt that once we had finished 3, someone would ask about 4. And so we decided we needed to come up with a better way to evaluate this function. And so let's just come up with a formula and fit the data that we have with a formula that we can evaluate quickly, and hope that that formula is, pretty good at approximating what we would have gotten using the finite element model. Um, so we had, say, 200 or so data points right now. And then we did a few hundred more. So maybe we have 400 data points in the end. And we decided we're going to fit a function to this data. We strategically chose the data points. They weren't randomly generated or anything like that. We knew what we wanted to look at. And so the first approximation is always linear. Try to find a linear function. So if I have 20 variables, a linear function is going to have 21 undetermined constants. And each data point represents an equation to help determine those constants. So we have 400 equations and 21 unknowns. There's a pretty close to guarantee that there's no actual solution to that. But we can do like a least squares fit. You can solve the normal equations and determine the best coefficients in a least squares sense. So we do that, and so we have a linear function. We had about 400 data points, and we really didn't need all that many to generate the 21 unknowns. So we decided to crank it up a notch, to look at some quadratic terms, to try and get a better function representing what the finite element model would have told us. So we did the quadratic, but we didn't do every quadratic term. So if I had 2 variables, x and y, I would certainly want x times y in my list of quadratic terms, because that represents how 2 variables might work together to either contribute or detract from the performance of the joint. But x squared and y squared create problems, because they might introduce a maximum or a minimum on the inside of the interval. And that would be, we've already discussed, that it's probably monotonic with respect to each variable individually. And so that maximum or minimum would be an artifact of our approximation and not representative of the physics of what's happening. So we decided just to use what we call the interaction terms for the quadratic terms, the x times y terms. And there's 190 of those. It's 20 choose 2 again. So we have 211 unknowns. We have 400 data points to determine those. So we had what we needed, and we really couldn't go any further than that. And we'd kind of run out of time too. So we make these 2 functions. We call them surrogate response services. They are surrogates for the actual model. And we wanted to see how well did they do in reproducing the data that we had. So that's what these 2 graphs are. So on the horizontal axis is what the finite element model predicted was the minimum charge size. And then on the vertical axis of each is what the surrogate model predicted. And in a perfect world, everything would lie on that line, y equals x. And you can see it's clustered there. The quadratic one does slightly better, but it gets us in the ballpark, and we can evaluate it quickly. So now when we want to do 1,000,000 designs, we can do 1,000,000 designs. But we have to be careful how we interpret the results, because this is an approximation of the finite element model, which is an approximation of a laboratory specimen, which is an approximation of an actual joint. So we're removed many levels from quantitatively telling you what the minimum charge size is. The usefulness of what this is now I can randomly generate designs, 1,000,000 of them easily, and evaluate the minimum charge size, and then identify outliers. So I can find designs that would be predicted to do really bad. So that's what we did. This would be one run of our Monte Carlo simulation, where we attached a distribution to each of the variables. We randomly generated designs, evaluated the minimum charge size, and we come up with this histogram of what the minimum charge size required would be. And it's a distribution. It has a mean and a variance. It looks very normal. But what's important to us isn't those quantities. What's important to us is the outliers. These things that required a lot of charge, because what those represent are designs that are trouble. And so what we would do, there's, only a handful of those. We can build the model for those designs, for those few designs. That's not too much trouble. And we can verify that they do require a lot of charge. And then we can spend our efforts either in inspection to guarantee that those variables are not pushed to those limits. And usually it was a combination of variables. It's not, an individual variable at its limit. And we can also spend a little bit of our effort in controlling the tolerances on those levels in production. But that's where this effort, what it informed. So the finite element model was not taken as reality. It informed us on where we could spend our further effort to make a more reliable frangible joint. And I check my watch here. I'm close to the end of the time. So I'm going to go back for a second and to the previous slides. That's sort of a day in the life of a finite element analyst. And I think the thing that sticks out to me, having taken the finite element course, having taught the finite element course, and also helping other colleagues, who are taking it in grad school or something, I didn't put up a differential equation. You did not see a differential equation there because it's kind of moot to the finite element analyst. And when I talked about, I had, talk about the class and I talk about what the software does, I think there are certainly differences in being a finite element analyst and learning the finite element method in school. And I think the largest chasm is that it's a math class. You're learning how to approximate differential equations, but when you're using the software professionally, you're doing some engineering and you're actually better prepared to use the software by learning about CAD, computer-aided engineering, because that's the language that a lot of the software manuals are written in, and a lot of the things you need to, if you want to look up how to do something, you need to know that. And just putting your hands on the software and building a model, knowing how to, having experience with CAD would better serve you. And in fact, I've talked to a lot of my colleagues and very few of them are aware of the differential equations being solved. And there's even some unaware that differential equations are being solved by the software. They know it's making some sort of approximation, but to use the software effectively and efficiently, it's extra. It's something that's nice to know, but it's not really going to help you in your day-to-day job. But that's as a finite element analyst, not as someone writing the software. So I guess I'm done. I can answer any questions, respond to any comments, or just
yeah. So when Rich was at West Point, he gave a set of talks on finite element methods, and between that and other readings, I mean, basically you're cutting up the object you're working out into little dots or nodes, and you're connecting them each with a spring, and each of those springs has a differential equation, and you're modeling the forces on those. Was that a bad analogy, or?
That's actually probably how most engineers understand it.
Okay.
But yeah, so you take the domain of the differential equation, you divide it up into really small pieces called elements.
Yeah.
And then you make it a very simple approximation to the differential equation on the element.
Yes.
And then there's this bookkeeping involved where you need to reassemble all the elements together into the whole domain and make sure that those approximations agree on the shared boundaries. So that's the 1 minute finite element course. Yes.
Yeah. So the point is, this could be an interesting topic for students to investigate, whether they're engineers or not. Animation uses it a lot. I mean, Yoda's robe in Star Wars is an example of finite elements. How a robe drapes over something. Yes. Together with. And so, and Rich's point earlier about there isn't anything we look at that hasn't been created by finite element methods. I'll go one step further and I'm going, look around the room you're in. There isn't anything in that room, for the most part, that hasn't been built by engineers. And so when you come from a liberal arts setting like I did, having taught our next speaker, Jeff Alden, to a place where I work with engineers, my respect for engineering just went up incredible. Any questions about how you, do you want to say just a quick flash about your background? I mean, you have a mathematics rich background and a PhD as a mechanical engineer, right?
Yeah. So I wandered a bit in school, but I eventually finished with a math degree and as a BS. And then I went to grad school and I got my master's in math. And at the start of the PhD program, I was offered a fellowship to switch over to engineering. It was the mid-90s. It was a very bad time for math PhDs. There were too many PhDs and not enough faculty positions. And so there was an article in AMS or something about that. And my department took it seriously and were very helpful I was at a big, large land grant university, so there were many other departments where we could go, and they actually found funding even for me to go to mechanical engineering. That you may think they're trying to get rid of me, but there's very little doubt that it has helped me out quite a bit professionally.
There's a downside to that, and that is when you go with a mechanical engineering PhD and apply for a job to a math department, they go, boy, we don't like your kind because you're not like us.
That's absolutely true. Yeah, I've actually been told at the second interview, because they didn't investigate it, that they were legally obligated to hire someone with a math PhD because that was what was put in the posting.
Yeah. Well, I think what we're about to see is that these people in mathematics move into these fields and they don't lose their math identity, but they don't necessarily wear it on their shoulder. And a lot of people don't know how rich and deep their background is. So we're thankful for Rich for sharing that. And we wish him well and for coming along on our journey. Thank you very much.
Thanks for inviting me, Brian. This has been fun.